coming back, this is the second part or the second session of the first part of a series of lecture in Nonstationary Time Series Analysis with modern signal processing techniques. Okay, so just a quick recall about the rough topics to cover in part one. Okay, so it has been discussed yesterday. And also recall the overall goals and challenges. The goals is somehow similar to what we want from the general signal processing topics. And as you can see, the learning part is actually like the machine learning part, which we care about nowadays for artificial intelligence. But we need to, before we can enter that, we have to face several challenges. Okay, so today in this session, the topic will be mathematical model for biomedical signals. And there's a subtitle, okay? This kind of model holds for other signals, not only in biomedical field, but today we will focus on biomedical signals. There are a few types of common oscillations that we encounter in practice. For example, the sinusoidal function or harmonic function. I mean, you can see it oscillates very regularly, like a sinusoidal function. This is the harmonic function or sinusoidal function, which is very, very beautiful. There's another thing called frequency modulated signal, or it oscillates with instantaneous frequency or time varying frequency. As you can visualize, the signal oscillates slowly in the beginning, but faster in the end. That's called frequency modulation or instantaneous frequency or oscillation with instantaneous frequency. And you can also see that this signal oscillates smaller in the beginning, but larger in the end. Okay, so this is called amplitude modulation. And for this amplitude modulation function, usually we care about is instantaneous amplitude. And you can make things more complicated. But before that, let's take a look at the frequency domain or the spectrum of this kind of frequency modulated signal or amplitude modulated signal. You can see this frequency modulated signal in the frequency domain. It has some weird behavior, but as you can see, the frequency has some kind of spreading, okay, ranging from roughly 1 time per second to like maybe 5 times or 10 times per second. So you can see the peak ranges from 1 to roughly 10. And you can also see this amplitude modulation, which you can see its frequency domain is like a peak, but spreaded one. Okay, this guy is easy to understand. As you can see, this is a function that can be modeled by a cosine function multiplied by an amplitude function. So multiplication in frequency domain, multiplication in the time domain is equivalent to convolution in the frequency domain. So the frequency domain, what you get is the peak at 3 Hertz, which is the original underlying oscillation, and the convolved with the spectrum, the spreading of the amplitude of the amplitude. And this guy, if you do some calculation, if this is if it is really a chirp function, then you can do precise calculation using Gaussian integration, and you can see precisely what it is. But in general, it's more challenging to understand its power spectrum. And you can combine both, for sure. You can make it both simultaneously amplitude modulated and the frequency modulated. And as you can imagine, the spectrum behavior is more complicated. And let's take a look at a real signal. This is a real respiratory signal recorded from nozzle. This is a air flow signal. As you can see from this signal, just by eyes, you can see obviously the oscillation here is larger, okay, with larger amplitude. And the amplitude is smaller, around 150 seconds. That you can see easily. And you can also see that the oscillation here is slower, but oscillation roughly here is faster. All this do not need any mathematical analysis. Just by eyes, you can see it. The question is, we see it, but how to quantify it and how to study it. And you can see small, big, fast, right, and slow. And now we have this behavior. How about its Fourier transform? Its power spectrum looks like what I showed below. You can see that, well, there is a peak here, right? 0.2 something 1 hertz, which tells us that roughly every 5 seconds you have one cycle, one oscillation. But there are several crazy spikes and so on, neighboring. What are they? What can we say? Actually, power spectrum in general can only give you the average rate, but we cannot get too much more. We can also use the phase information, but the phase information is also global, so which makes the analysis more challenging. What we want, again, is how the amplitude changes from time to time and the frequency changes from time to time, or this kind of momentary slow, fast, or small, big pattern. That is what we want, but we cannot read it from the power spectrum. So we need some new tool. Okay. Oh. Okay, there are some technical issues here. Okay. And everything we have talked about, I have shown you above, simulated one, very simple one, or real one, the respiratory, more complicated one. They are all called single component. Single component. We will encounter multiple component signal in a bit, but all these are single components. Okay, ranging from the respiratory signal, frequency modulated one, amplitude modulated one. They are all single component signal. And this is the goal and the features in real-world database, which I have shown you. So just take a second look. Today, we will start from giving you a model and then continue with the goal, the zeroth goal, okay, and continuing everything during the lecture. And again, let me show you some more examples, which which we saw yesterday. For example, this is photoplethysmography. You can see it oscillates beautifully, but I can tell you there are two components. One is the cardiac component, about your heartbeat, but there is a slowly varying low frequency component, which is harder to see, but that is about respiration. And this is a peripheral venous pressure signal, which is from the venous, which actually contains cardiac component, but it's very difficult to see it because of the very complicated noise behavior. And this is transabdominal maternal ECG. In this transabdominal maternal ECG, you have at least two components. One is maternal's ECG, this big one, and another one is fetal ECG. That is the smaller one, narrower one. And the third one, this is an airflow signal. In this airflow signal, actually there are two components. One is respiration, another one is about cardiac component, which is called cardiogenic artifact, which we will discuss and see how to use it in a bit. Okay, so now we have seen enough examples, and I have told you enough challenges and the goals. So let's start our journey about the model. Once we have the model, we can design algorithms. What will be the model? The simplest model, the first version we will discuss, is called adaptive harmonic model. It has the following form. You have y of t, which is actually a random process, but it is a non-stationary one, where you have a summation of k components and ai of t, cosine 2 pi phi of t, plus capital T of t and the sigma capital phi, which looks very complicated, but let's take a look at this one by one. This ai of t is amplitude modulation, which we assume will change slowly in this sense. Its derivative will be much smaller than epsilon times phi prime, which I need to introduce in a bit. And the phi of t, which is a monotonically increasing function, and that is called phase. Okay, and in this monotonic increasing function, we have a condition that its derivative is positive, so that we know why we can control it. And this phi of t is called instantaneous frequency, which we also assume that will change slowly in the following sense. That is, the amplitude modulation change and the instantaneous frequency change will be much smaller than the instantaneous frequency at the rate epsilon, which is determined by you as the model designer. Epsilon usually is small. And we call ai of t cosine 2 pi phi of t, the I is intrinsic mode type function. And if you pay attention, suppose ai of t is a constant. This is constant. And you have phi of t is 2 pi cosine t plus beta I, where beta I is in between 0 and the 2 pi cosine positive. Then what you get will be ai cosine 2 pi cosine t plus beta I. And this is what? This is the traditional harmonic function. This is the traditional harmonic function. And in this traditional harmonic function, you will see that ai is usually called amplitude, cosine is the frequency, and the beta I is usually called the phase or global phase. So what we are doing there is we combine these two terms, 2 pi, and we call this guy usually the phase function. And our goal is to generalize this kind of signal to this time varying natural type of signals. I hope it is clear on the blackboard. And the capital T of t is usually called the trend, which we assume will change very, very little locally. It doesn't change fast. You can consider, oh, trend is something very much like a constant function. Mean, that's usually a very the simplest trend. But also, mathematically, you will assume that its Fourier transform in the distribution sense is actually supported very closely to 0. It's supported around just 0, so that it does not have spectral leakage to the high frequency domain. And in this sense, which we will discuss in a bit detail when we need to handle trend, in this sense, polynomial is actually not a good one if it's not a good one to model trend in practice, in particular when the data signal is short, it's very short. Okay, because in the frequency domain it has a very strong spectral leakage. And we need to be careful when we use polynomial when data is very short. We need to do some fitting. That is, it will be another story. And the capital Phi of t is a stationary noise. For example, you can consider a traditional AMA process. And the sigma t is a non-stationarity that characterizes how the covariance of the sigma t changes from time to time. And the mission, signal processing mission we have here is that I give you one realization of this random process, only one realization, okay? And I want you to decompose all these components for me out of one realization of y. That will be the mission. And that is what we will discuss and achieve in this series of lectures. And certainly, once we get this, then they are the so-called features we like for data analysis or signal processing. So this is an example. I give you two oscillatory components. You can see visually this one oscillates faster, this one oscillates slower, and this doesn't change too much locally. This is a trend, the first component, second component, and I sum them together, I get this signal. So this is a very, very, very simple simulated signal, but I want you to reverse the process of this summation and get these three components out of it. For me, that will be the mission. Oh. Okay, so this is a visualization of the impact of instantaneous frequency and the amplitude modulation on power spectrum in real data. Well, relatively real, this is semi-real. For example, you can see the signal. It has some nice oscillatory pattern, and all the intervals, peak to peak intervals, are 1. Okay, so this has a fixed frequency, and the amplitude is also fixed. And now I do some modulation. Okay, I change the period. I change the period from 1 to varying times, and also you can see the amplitude changes, and there will be some kind of baseline wandering or trend. Okay, now you can see in the power spectrum of the original signal, it's very beautiful. 1, 2, 3, and so on. 3 harmonics. But here you can see, oh, there's 1, 2, 3, 4 maybe, but there are a lot of spread. And this is exactly the same situation we discussed before. And there's a very interesting mathematical practice you can play with using trigonometric identity. So you know that if I give you a cosine 2 pi ft plus bt, then you can easily decompose it into 2 components. There's nothing really much to say, right? But you will see that this kind of amplitude modulation, cosine, okay, multiplied by some amplitude, multiplied by some oscillation, and this sine multiplied by another oscillation. This is yet another way to represent this cosine function. So once you have a sinusoidal function with angle modulation, it can be written as 2 amplitude modulated sinusoids that are offset in phase by 1/4 cycle. Okay, that is a very simple. Just if you ever went to junior high school or senior high school, I forget, you will learn this, how to play with this game. But the question is, which one is better? Why do you prefer one instead of the other? For our purpose, okay, for the modeling purpose, you can see this this picture as another example. I give you a very simple cosine function. Again, super simple, but it is easy that you can change amplitude modulation function by adding an alpha of t function to 1. And then you change the phase function to be t plus beta. So that amplitude modulation looks like this guy, and the phase looks like this guy. But these two guys are very, very different from the original 1 and t that I believe we all agree upon. But now I can tell you, if you take this amplitude and this phase, you can reconstruct exactly the same cosine function. Now the question is, which one is better? And why do we prefer one than the other? So this is the identifiability issue, which usually you need to pay attention. And there was some theoretical results that is under adaptive harmonic model condition. Okay, we can say that suppose you have 2 representations of the same component, and let's assume there's only one oscillatory component, and we denote the difference of amplitude modulation to be alpha and the phase to be beta. And I assume, again, both of these representations satisfy the adaptive harmonic model conditions. Then what we can show, okay, which I will not go through proofs, but you can check the proof in the paper, up to somehow a global factor 2L pi, which is a global factor. Actually, the phase and the amplitude of both components, they are almost equivalent, and they are different only up to an error of order epsilon. And this is a very kind of a bit annoying result, because then you will say, what do you mean by epsilon? Because when epsilon is large, then we lose the control. But when epsilon is very, very small, then we can control it, but still we have some epsilon. Then what are we talking about? you can think it a bit like an LP function. Okay, LP function is actually, when we say LP function, it is actually a set of functions. Okay, but all these set of functions can be different, and they are different, but they are only different up to a major zero subset. Okay, but here it's no longer a major zero subset. It is different up to some order epsilon. And the situation is very peculiar for the real form function. If the function is of complex form, then the situation, the story is different. For example, right now, if I give you 2 pi phi of t, suppose this is a complex form. Is this function uniquely defined? Answer is yes, right? It's uniquely defined. Actually, if you consider amplitude, take modulation, then you get the amplitude modulation. Okay, and then you just consider the division. Then you get exponential I to pi phi of t. And once you get here, you can easily get phi of t up to 2 pi along globally recovered. So the phase is usually unique up to some kind of 2 pi along, and amplitude is always amplitude unique. So this is very, very peculiar behavior when you have complex form. But usually what we have is a real form. It's a of t cosine 2 pi phi of t. This is a bit, okay. In this case, the situation changes. That is, we lose the control in between zeros and 1. And that is the part that you need to pay a bit attention why we introduce all this TM, SM, and some kind of controls. But in the end of the day, we use the epsilon to control everything. So this identifiability issue is somehow resolved by taking the theorem into account, which means we can always recover things up to some error of order epsilon uniformly globally. Okay, and the similar theories hold for functions with multiple components, which you can check. And this is a statement only for one component. Okay, we could thus define amplitude modulation and instantaneous frequency unambiguously up to an order of epsilon.